Welcome, everyone, to the Institute of Navigation webinar, Signal Quality Monitoring based on Chip Domain Observables, Theory, Design, and Implementation, published in the winter 2022 issue of Navigation. Today's webinar is being presented by two of the paper's authors, Professor Mingquan Liu and Professor Xiaowei. Dr. Mingquan Liu is a professor and director of the Positioning, Navigation, and Timing Research Center at Tsinghua University, China. He has been engaged in teaching and research of the Chinese Beidou navigation satellite and global navigation satellite system for 2 decades. His research interests focus on the theory and implementation of Beidou signal processing. Dr. Xiaowei is a professor of the Positioning, Navigation, and Timing Research Center at Tsinghua University in China. He has been engaged in teaching and research of the Chinese Beidou navigation satellite system and global navigation satellite system for nearly 2 decades. His main research interests include Beidou's GNSS signal processing and receiver implementation. You can download this paper and many more on the Navigation Open Access website found at navi.ion.org. The website has tools that allow you to read, download, cite, and share valuable research content such as this paper. So thank you for being here, and now we'll turn it over to our presenters.
Thank you, Rick. Good morning, good afternoon, and good evening. Thank you for your attention. I am Xiaowei from the Department of Electronic Engineering of Tsinghua University. It's my honor to introduce our latest work in signal quality monitoring. This work was published in Navigation last year. The title is Signal Quality Monitoring based on Chip Domain Observables, Theory, Design, and Implementation. This is the content of today's presentation. First, the background and the motivation of this work is given. It's well known that GNSS has entered the era of compatibility and interoperability, thanks to the ongoing modernization of GPS and GLONASS, as well as the rapid development of BDS. The 4 major global navigation satellite systems provide positioning, navigation, and timing services to users in growing number of application fields. However, for some safety-critical applications, there are still more stringent requirements in terms of accuracy and integrity. This table lists the signal in space performance requirements for typical operations of civil aviation. It's not difficult to find that these requirements exceed the committed performance of GNSS core constellations, especially in terms of integrity. To solve this problem, several types of augmentation systems have been developed, such as SBAS, GBAS, and SBAS. Let's take SBAS as an example. SBAS is an integrated system composed of reference station network, master station, uplink station, and geo satellites. SBAS broadcasts wide area differential corrections to improve the accuracy and introduce many monitors for various types of faults to enhance integrity. In this way, SBAS can provide continent-level coverage of high precision and integrity service to civil aviation. The potential risks to be monitored in SBAS include clock and ephemeral error, code carrier incoherence, ionosphere scintillation, signal deformation, and so on. In this work, we focus on the monitor design for signal deformation. The first observed event of signal deformation is GPS SVN 19 event in 1993. The differentially corrected vertical prediction error is up to 8 meters when SVN19 was included in the solution set. Which compared with error on the order of 50 centimeters when this satellite was not in view. From the figure on the right, we can see a sharp spike on nominal power spectrum. After fault analysis, this abnormal event was found to be caused by the onboard hardware failure. Since then, the research on signal quality monitoring had begun, and the term signal deformation is used to refer specifically to the evil waveform that is caused by the onboard hardware failures. Let's look at the effect of signal deformation on the receiver. It's easy to understand. A distorted signal may deform the correlation function. Then the deformed correlation function might cause Schulder's biases. And finally, the Schulder's bias might induce a large partitioning error. Meanwhile, above analysis also shows that the shape of the correlation function can be used to indicate whether the signal is distorted. This is the working principle of the classic SQM method based on multi-correlator observable. It forms some detection metrics based on the correlator outputs in the receiver. The MCO-based SQM was standardized in EchoSAPS. It had been operational for nearly 2 decades and performing well in single-frequency SBAS. The next generation of SBAS will incorporate dual-frequency multi-constellation techniques. Multi-constellation provides observation redundancy, and the dual-frequency ionosphere-free combination would eliminate first-order ionospheric error. It's expected that DFMC can better mitigate potential integrity risks and promote availability for safety-critical applications. However, this kind of dual-frequency combination will inflate any biases in its single frequency. According to Professor Todd Water, the ionosphere-free combination has roughly 3 times as much noise as either single frequency term. This is the penalty paid for removing the ionospheric error. Because the signal deformations are unlikely to be identical on both frequencies, the effects may be greatly magnified compared to single frequency. Thus, signal deformation might be the largest source of uncertainty in ranging error after first-order ionospheric delays are eliminated. So DFMC puts forward more stringent requirements to SQM. However, it's difficult for traditional MCO-based SQM to meet the requirements of monitoring signal deformation in DFMC dual-frequency mode. The filtering effect of the correlation process is the main reason of limited detection performance of MCO-based SQM. It might average down some distortions. This enlightens us whether we can skip the correlation function and directly watch the distortion from the chip shape. This idea leads to the so-called SQM based on chip domain observable. In this paper, we systematically studied the theory, design, and the implementation of this emerging SQM technique. Next, we give brief overview of SQM. As mentioned earlier, if an evil waveform was received, the cross-correlation function of the distorted incoming signal and the nominal local replica would be deformed. These figures show an example of a simulated GPS L1CA signal with distortions. 3 receivers have different correlator spacings and induce different ringing biases. Since signal tracking is sensitive to receiver configurations, signal deformation could invalidate or even worsen the differential process in SBAS. In order to protect different types of user receivers, signal quality monitoring function is necessary to be introduced in SBAS reference station. There are 3 external conditions for the design of a SQM method, include the modulation types of protected signals, the evil waveform model and its space, the constraints on the configuration of protected receivers. This table shows the structure and the modulation of GPS L1CA, BDS B1C, and B2A signals. These 3 signals have the representative modulations and chip rates in the context of DFMC. Since 2000, EchoSARs have been applying the second-order step model as the standard threat model for potential signal distortions. This model classifies the signal distortions into digital distortion TMA, analog distortion TMB, and combined distortion TMC. Here are the threat spaces for above 3 signals. These have been standardized and newly adopted by Echo. Receiver configurations might have effects on both ranging and signal domains. In compliance with the specification of Echo DFMC draft, reference receiver configuration and the user receiver configuration space are shown in this table, including the discriminator type, the correlator spacings, the pre-correlation bandwidths, and so on. Next, 3 concepts are defined in the ranging domain to embody the criteria of SQM performance. First, max PRE is the maximum of the differential pseudo-range errors obtained between the reference receiver and its specified user receiver toward a particular signal. Second, MUDE is the maximum of the max PRES obtained from all possible signals that are not asserted anomalous by SQM. It represents the protection capability of a specific SQM method. Third, MER is the max PRE value obtained with the worst satellite geometries without resulting hazardous misleading information to users. It represents the application requirements to the protection capability of SQM. To summarize, the overall objective of a SQM method is to guarantee that the MUDE from the given thread model, thread space, and the receiver constraints does not exceed a specified MER value under particular integrity requirement. Now we will describe the design theory and the methodology of SQM based on CDO. The design of SQM method is affected by both the conceived SQM operation mode and the performance requirements of the protected application. The proposed methodology consists of iterations of algorithm design, algorithm assessment, and the potential simplification or optimization. The relationship among the SQM design modules are shown in this figure. An operational procedure of CDO-based SQM method includes following steps: raw CDO measurement, CDO normalization, metric calculation, metric smoothing, determination of nominal metric value and the standard deviation, and the final detection. First, raw CDOs are measured when the tracking loops are locked and the carrier wipe-off process is performed. Each individual chip is segmented into M bins to obtain M raw CDOs. Every raw CDO measurement is the average of the digitized sample points within the corresponding bin across a given integration period. In this step, 4 influential factors are incorporated, including the integration period, the proportion of a code phase bin to a chip, the sampling frequency, the pre-correlation bandwidths. At present, extracting the raw CDO measurement can be realized on both hardware receiver and the software receiver. In 2005, Vision correlator designed by Noatel first introduced the concept of chip shape observation. And our lab has implemented the chip shape correlator based on the signal compression technique in our real-time software-defined radio receiver. Then the raw CDOs are normalized by the in-phase component of prompt correlator value. This normalization process can also eliminate the impact of an removed navigation bits. In this step, the 5th influential factor is the signal amplitude. Next, N-raw metrics are obtained by using various elementary combination of the M-normalized CDOs at the current epoch. According to relevant analysis, CDOs on rising axes should be utilized in metric definition to better reflect the magnitudes of signal distortions. So the 6th influential factor, the rising edge rate, is the ratio from the quantity of rising edges to that of chips within one code period. To further mitigate thermal noise and multipass on raw metric values beyond the given integral accumulation for each epoch, metric smoothing process is carried out. In this step, the 7th influential factor is the metric smoothing time constant, TMST, or equivalent, a site-dependent smoothing improvement factor, SIF. The determination of nominal metric values and the standard deviations is based on long-time observations, and all such values are elevation dependent. The polynomial fitting coefficients can be determined statistically by the Gaussian overbounding method and then pre-stored. Consider the elevation angle is positively correlated with the carrier-to-noise ratio of the received signal. In this step, we select the carrier-to-noise ratio as the 8th influential factor. Finally, at each monitor epoch, a figure of test for the untested metric values is obtained. If the figure of test is larger than 1, the monitored signal should be asserted anomalous. In this step, the 9th and the 10th influential factors are involved, namely the Gaussian quantile of the required false alarm probability and the number of reference stations to provide averaging gain. This table summarizes the 10 influential factors involved in the operational procedure of CDO-based SQM. Therefore, the design goal of a CDO-based algorithm is to seek the optimal configuration of these factors to achieve satisfactory performance meeting the requirements. The general operational procedure just introduced provides guidance for CDO-based SQM design methodology. The designed SQM method should be fully assessed, and further design iterations with metric tests may be necessary for simplification or optimization. This figure shows the detail of proposed design methodology, including a more general macroscope design flowchart in the upper yellow boxes, and a macroscopic design method within the large black rectangle at the bottom. First, the 10 factors are classified into 4 categories. Specified factors are fixed throughout the whole design process according to echo subs, including the integration period, the pre-correlation bandwidth, and the nominal scale multiplier. Dependent factors are also fixed for corresponding signals. Smoothing-related factors are set for smoothing process, including the metric smoothing period and the minimum number of stations for reference averaging. Finally, featured factors are relevant to SQM performance, but are not specified, so they must be designed. They including the proportion of a code phase bin to chip, bin length, and the sampling frequency FS. Because the closed form expression of either nominal or deformed metric values cannot be precisely derived using the thread model. The design and optimization of these featured factors need to be solved by massive simulations. This figure illustrates the designed framework of the verification platform and can be applied for massive simulations of SQM design. For its specific signal, the simulation is carried out at 3 levels. At the signal level, the simulations are carried out across the anomalous signals caused by the discretized thread space. At the channel level, for its particular point within the discretized thread space, the distorted signal is processed by both the reference branch and the user branch simultaneously. At the calculation level, 2 examinations called monitoring and max PRE estimation are incorporated. The performance of various bin and FS combinations are obtained via simulation across the discretized thread space for a specific signal. Based on these results, optimal bin length can be derived. Then, with the optimal bin, a trade-off between sampling frequency and the smoothing process would be made to supplement enough gains for the required performance. Next, we will demonstrate a design process for CDO-based SQM baseline algorithm according to the methodology described in the last section. For simplicity, baseline algorithm directly use 8 CDOs around the rising as raw metrics. At the beginning, we treat the metric smoothing and the reference averaging as independent gain contributors, so the bin and FS are left as the design variable. The verification platform is utilized to obtain performance with this setting for different combinations of bin and FS. Then the optimal bin will be derived for specific FS. After finding out the optimal bin length, we integrate the gain of metric smoothing and look for the minimum number of reference stations participating in the average. In this way, the design problem of baseline algorithm is simplified to determine the optimal bin length and the minimum number of reference stations for different GNSS signals and different receiver sampling rates. Based on the specific selection of detection metrics in the baseline algorithm, we can derive a figure of merit to directly examine the relationship among these design variables, where CMB is the metric bias of the thread point that is hardest to detect. That is to say, the fundamental purpose of massive simulation is to find out the CMB corresponding to the specific bin and FS combination. All design parameter combinations that can ensure this figure of merit greater than 1 are acceptable. With simulations across the ranges of bin and FS, we get the contours of this figure of merit. Then we determine the optimal bin length for baseline algorithm is 1/40 of a code chip for L1CA and B1C signal. Next, we use L1CA signal for assessment of the baseline algorithm performance with 2 sampling frequency as an example. The simulation results show that with a sampling frequency of 33 MHz and 3 stations for averaging, baseline algorithm can achieve the minimum equivalent carrier to noise ratio that meets the SQM performance requirements and the DFMC SBAS, while with a 66 MHz sampling, only 1 station is needed to guarantee the safety. A step further, we compare the performance of CDO-based and MCO-based algorithm. From this figure, for L1CA signal, when the sampling rate is higher than 24 MHz, the performance of CDO-based algorithm is better than that of MCO-based. For B1C signal, the advantage starts from 33 MHz. Considering the convenience of increasing sampling frequency in modern receivers, the CDO-based SQM algorithm is expected to have great potential and could perform better than MCO-based. Finally, concluding this study. First, aiming at mitigating signal deformation risks for safety-critical user and the DFMC SBAS criteria, we proposed a design methodology for CDO-based SQM methods on the basis of derivation, simulation, and simplification. Then a complete and general baseline algorithm was designed in accordance with the proposed methodology, and its performance was confirmed. Therefore, the proposed design methodology of CDO-based SQM method provides a paradigm for particular signals towards given requirements. This is the end. Thank you for your attention and listening. You may check out our full paper throughout this link. If you have any questions, you may ask in the later Q&A section or just contact us after this webinar. Thank you.
Okay, thank you very much, Professor Cui. Maybe our topic is not enough interesting. So far, there is no question in the Q&A box. I don't know, is there any question? Okay, so we ended the Q&A session. Anyway, we are very pleased that ION conducted today's webinar. Let's have this opportunity to introduce our research work. Rick?
Thank you both for being here. We appreciate this great presentation. And this presentation will be recorded, made available on our YouTube channel and on the website at ion.org. And our presenters also have their email addresses displayed here. So if you have questions, you can contact them later. Thank you both for being here and have a good evening.